Okay, so we are discussing hidden Markov models, and we saw 3 problems in hidden Markov models. The first problem is sampling. Like given a model, how do we sample new data from the model? Second problem we saw was inference. Given the model and given the observations, how do we classify the states, the hidden states, right? So which means given the model, given the observations, how do we know all the states? Then the third problem we are discussing is training a new model. We have the data to train and we have our model. Now we want to train our model with the data. Okay. So for any training problem, we first formulate a loss function or objective function, right? Objective function is generally maximized and loss function is generally minimized. So we make an objective function and we try to maximize it with respect to the parameters of the model given the data. So we have our, let's say L is my loss function or the objective function. We saw in our previous class that we defined our loss function as the MAP or MLE. Which one? MLE. Because we said that if we do MAP, we need a prior estimate on theta, and we may not have a prior estimate on theta, so we can work with MLE also. So we actually started with MLE estimate. If you have a prior estimate of theta, you can incorporate it. Then it becomes like the MLE term or the likelihood term multiplied by the prior term. So the optimization or the training algorithm remains similar, but just that you have an extra prior multiplied. So for general case, we are discussing MLE, which is L of theta. Theta is the set of all the parameters inside the hidden Markov model. So this is equal to log of P x given theta. So here x is the all the observations, x1, x2, x3, x4, that the entire sequence that is clubbed into this variable capital X. And then we did some, to introduce some z, we did some marginalization over z, and we said this is equal to log P x comma z given theta. Oh, sorry, it's not like that. The summation comes over here. Okay, we ideally want the summation to be outside. We don't want it inside the likelihood, inside the log, because log of a plus b is just log of a plus b. But if it were log of a into b, then we could have written log of a plus log of b, and then optimizing it becomes very easy, just differentiate and optimize, etc. But this one, optimizing is difficult. That's why we did some trick which is called the EM algorithm to take the summation sign out of log. So we said this L theta is greater than or equal to summation over z q of z given x comma theta old and log of p x comma z given theta. Right? This is what our L theta became, and then this term, let us call it as q of, this is q of theta comma theta old, some capital Q. It's not small q. Small q is probability distribution probability density function, but capital Q is just a loss function, right? So some Q of theta comma theta old. So if I can maximize this Q, then maximization of L is automatically guaranteed, right? That is the basic principle of EM algorithm, right? Huh? This one? This is actually, it could be any non-negative numbers which sum up to 1. And we choose it as Q of Z given x comma theta old. And in Jensen's inequality, it is just any non-negative alpha which sum to 1. But when we optimize it, we will find the value of Q, and that comes out to be P of Z given theta x comma theta old. So when we do EM algorithm to maximize Q or to find the theta, optimal theta, so in the E step, I find my Q. This comes out to be simply P of Z given x comma theta old. This derivation is already discussed in the class, right? EM algorithm has been discussed. So this part I'm not going to tell again. It's simple, very ordinary EM algorithm. You can go back to the notes and see. Then the M step. What is M step? In M step, we estimate theta. So my theta is equal to So actually this term Q is actually expected value when Z is sampled from this log P, right? This is expected value, right? This term is just the expected value. They are same. So basically this is equal to expected value right? All of you agree? The simple Monte Carlo approximation, or not even Monte Carlo approximation, this is the exact formula because Z is discrete random variable. Okay, that's it. So we find our theta by maximizing this. Okay, so in EM algorithm what happens is, first you start with some random Z, right? From that random Z you compute this term, right? It's simple, computing the probabilities of those Z, whichever you have assumed, right? And then you update theta with the previous Z, means the model, the theta old model, you use it to maximize your theta. Okay. It is similar to k-means approach, right? Do you remember EM algorithm? Roughly? Okay, let's compare it with just a quick recap. It has been discussed, but doing it again. In EM algorithm, what you do, you have to cluster the data, right? So you choose some random points as the centroids. So in the E step, you find the clusters, which means given this centroid, what all points belong to this cluster, right? So that is this E step. Given these centroids and the data, which all data points belong to this cluster, simply using Euclidean distance, right? And in the next step, you say, okay, now these are my cluster points. Let's update my centroid by taking the mean of these points. That is this step, M step. You update the means by, or the centroids by averaging the data points. And in this way you iteratively find the centroids as well as the membership function. Membership means this point belongs to which cluster. Right? So here you find membership, here you find update the clusters. Find membership, update the clusters. Find membership, update the clusters. Right? This is EM algorithm. It works for any discrete latent variables. Like here our Z is a latent variable, right? Z is a latent state. We don't observe it, it's latent, and it is discrete. So EM algorithm works here. Okay. So this was all kind of known to you, EM algorithm. Now let's apply this to HMM. How do we actually do it? So the reference for this discussion is the PRML book, the Bishop's book, Pattern Recognition and Machine Learning, and the section number is 13.2. Yeah, 13.2, and the title is Hidden Markov Models. You can read that chapter. It's very well written, very nicely explained. We are discussing Q theta comma theta old. This is equal to summation over Z, just copying from top. So I'm writing ln is like natural log. Whether you write ln or log doesn't matter. Okay, fine, log p of x comma z given theta. Okay. Now you want to do EM algorithm. So let's simplify this. This is a kind of joint distribution, but you know that you can break down your joint into factorized distributions. Let's do that. So let's take this P thing. So first we will break the P. Let me write it down like this. So this P will be broken up into probability of Z1 given theta into probability of Z n given Zn minus 1 comma theta times probability of xn given Zn comma theta. Right? So if we break it down like this, then this will also break down. So let's consider every term one by one, because it's log of product. So we can say log of this plus log of this plus log of this, right? So when we say these log thing, let's take the first term log of p of z1 given theta. Then in the qz thing, everything else will marginalize, right? Only the z1 term will remain. So it will become like this is equal to summation over z1 only. Z1 can take k values, right? Summer, winter, spring, and rainy. 4 seasons. So z1 can take 4 values. Means the weather today could be one of those 4 values. Times q of, instead of writing all the z's, now I can write only single z1. Why? Because others will marginalize. Right? It is q of z1 into q of z2 given z1, but then there is no z2 there, so it's a summation over z2 of all those z2 given z1, it will become 1, right? So in this way all other z's will marginalize to 1, and what will remain is only q z1 given all the data x comma theta old. So just for the sake of brevity, or just for saving some writing effort, I will not write theta old now, because it's whenever you have q, it's obvious that it is on theta old only, and whenever you have p, it is on theta, right? So p is on the unknown parameters and q is on the previous known value of the parameters, right? So I will, just to save some space, I will not write theta old again and again. Okay, so q z1 given x into log of p z1 given theta plus, this is the first term. Now the second term is involving zn given zn minus 1. So what will remain in the q term? In q, zn and zn minus 1 will remain. So I'm writing it as zn minus 1 comma zn given theta, oh sorry, theta, it's obvious, given theta comma x, so only x will remain here. Theta old is obvious, and into log of p of zn given zn minus 1 comma theta, right, plus, this is summed over what? Summed over all the z's, which means zn, zn minus 1, and you also sum over n, because this n goes from 2 to capital N, right? So sum n goes from 2 to capital N, and those zn and zn minus 1 will anyways remain, right? Your zn will go from summer, winter, etc. Zn minus 1 will also go from summer, winter, etc. Plus, now the final term is p xn given zn. So what will remain outside here? What will remain outside here? Q of z1 will appear. No, it will get marginalized, because inside there is no z1. Q of z2 also marginalized. What will remain finally? Only zn and so only zn will remain, right? Only zn will remain. The nth entry will only remain. So it becomes q of zn given x log of p of xn given zn comma theta, and summed over zn, and also summed over n. N goes from 1 to n, all the n's are covered, right? This is my objective function which I want to maximize. Is this clear? Any doubts here? Any confusions? So just a recap, we started from this formula, this was known to us, we kind of already knew this, and now just we are simplifying it. So we want to break this up using the HMM model, factorize it as per the HMM. So this is the factorization we know. Okay, there is a product here, which all of you know that there is a product here. Right? So that's why this summation comes. Okay. Now, some notations we can introduce. Whenever you have q of z1 given x, let's call it as gamma z1. So gamma z1 is equal to q of z1 given x. right? This is just a notation, and in general it can be written as q of zn given x is gamma zn, a general formulation. Then there is another term called q of zn minus 1 comma zn given x. Let's call this term as zeta. Okay, tell me the gamma zn, how many, for a given n, how many values does it have, or what is the length of this vector, if you call it as a vector? It's a PMF, right? It's a PMF. So what is the length of this PMF? Huh? No. It's not n. K. Yes, K. See, Z is, what is Z? Z is the weather. Weather can take 4 values: summer, winter, rainy, or spring. Right? So it can take 4 values. This is the PMF over those 4 values. It can take only 4 values. No? So it's a vector of length 4. How many degrees of freedom, or how many unknown parameters? 3 unknown parameters, because they sum up to 1. What about this? How many? This is a PMF over how many? What is the size of this vector or matrix, whatever? Huh? K square, yes. This takes k values, this takes k values, so we get k square values. K square is the size of this. So basically, gamma is a vector of length k, zeta is a matrix of length k square. But how many such vectors are there and how many such matrices are there? N, capital N, because small n can take capital N values, right? From 1 to capital N. This also can take capital N values. Okay, so this is the complexity or the space requirements. Okay, now let's define one more term. So this zeta zn can take k values from 1 to capital K. So which means gamma zn is a vector of length k. Let's call every element of that as gamma z n k. This is a scalar. Right? It is the kth entry in this vector. Okay? That's the notation. Kth entry of this vector. Now let's say this one has already also we need 2 indices to index it. So let's call it as zeta n z n minus 1 comma j comma z n k. This is the j comma kth entry of this matrix. Right? Easy? Clear? Okay, now what we want to do is we want to do EM algorithm with this. So first let us use this notation to simplify our equation above. So the original equation becomes equal to summation over z1. So now z1 can take k values, right? This z1 can take k is equal to 1 to capital K, right? So let's call it as summation over k. Then qz1's x is what? It is gamma 1k, gamma z1k times log of, what is p of z1 comma theta in the HMM? It was pi, right? Initial state probabilities. Pi k plus summation over n equal to 2 to capital N summation over Zn. Okay, now Zn and Z minus 1 are J and K. So summation over J, summation over K. What is the term Qn minus Qzn minus 1 Zn? What is that? That is zeta. Right? Times log of P Zn given Zn minus 1. What is this in the HMM notation? Transition probability AJK, right? AJK, probability of transitioning from jth state to kth state. Okay, then the third term is summation over n, summation over Zn. Zn is K basically. Zn goes from 1 to capital K. Q of Zn given X. Q of Zn given X is gamma Zn, and the kth entry is Znk. Gamma Znk times log of P xn given Zn comma theta. This is the emission probability, and emission probability can be written as P of xn given phi k. So phi k is the kth model, right? So for summers you had a Gaussian model. Consider like this example. For summers you had a Gaussian model. For winters you had a Gaussian model. Remember, this phi k is that Gaussian model, the means and the covariance matrices, or the means and variances of your Gaussian model, right? So for summers, what is the probability? For winters, what is the probability, etc. Clear? That's it. So we are now able to write everything in terms of our known notations. Now let's apply the EM algorithm. So basically theta was pi vector A of phi. Theta was a set of all the variables. Okay. Now let's apply the EM algorithm. Let's first apply the M step. M step means I know Q. I know theta old. So I know the probabilities of any data. My model can tell the probabilities, right? So which means I know gamma and zeta. Yeah, they are known. Right, we have previous model which we can use to compute gamma and zeta. Now, given the gamma and zeta, how do we update our model parameters? Tell me the estimate for pi k first. What is the estimated value of pi k? What is the estimated value of pi k? How will you estimate pi k? You've done Gaussian mixture models, right? You know how to optimize. What will you do? Differentiate this loss function with respect to pi k and find the value of pi k which maximizes it. Right? That's what we do, no? To estimate the parameters given the loss function. This is our loss function. To maximize it, we will just differentiate with respect to pi k. Can you do that? Can you do that quickly? Differentiate it with respect to pi k and then tell me the value of pi k. All of you know what is pi k? It is a probability distribution, no? PDF, probability density function, or PMF, probability mass function. So which means all pi k's are greater than 0, less than 1, and they sum up to 1. Okay, do it. So maximize the Q with respect to pi k. Pi k is the initial probability. What is, like, I'm starting my counting today. What is the weather today? I'm starting my experiment or measurements today. So what is the weather today? I don't know what was the weather yesterday, so I have to start from today. So that is pi k. Done? 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 Very simple differentiation. Done? What is the derivative of Q? What is the derivative of Q? Yeah. What is the derivative? This is equal to 0. Can you compute pi from there? You can't compute pi. So you know the constraint that pi sums to 1. Should you not add a Lagrange multiplier? Right? So we add a Lagrange multiplier saying that lambda summation over pi k over all k, basically k equal to 1 to capital K minus 1 is equal to, basically this is the lambda, right? So whenever our values are constrained in some way, we add that constraint as a Lagrange multiplier using Lagrange multiplier. So now you can differentiate. Now you differentiate. So what is now derivative of Q with respect to pi k? This is equal to gamma z1k divided by pi k plus lambda times 1, this is equal to 0, right? So pi k comes out to be how much? Gamma z1k upon minus lambda. How will you compute lambda now? K dash कहाँ आएगा? Yeah, for a particular k. Okay, ठीक है. K dash. Okay. This is for a particular k, so it's k dash. All right. K dash होगा ना. Our new variable that we want to find, that is what we take as k dash. Okay, so how do we find the value of lambda now? Add them. add them to 1. Yes. So let's start from this equation. You have lambda times pi k dash is equal to, with a negative sign, gamma z1 k dash. You take sum over all k dash. Then what do you get? This is minus lambda because pi k dash sum up to 1, and this is equal to summation over k dash gamma z1 k dash. So therefore pi k, now since there is no k, so I am just replacing k dash with k here. So my pi k comes out to be gamma z1 k divided by summation over all k gamma z1 k. Oh sorry, let's take it as k dash only. This summation thing is a dummy variable, no? It has no relation with this k. It's a dummy variable. That's it. So this is my answer. This is my maximum likelihood estimate of pi k. Can you find now the ML estimate of AJK? Find the ML estimate of AJK, or whatever is the, like, maximize this Q to find the estimate of AJK. What is the constraint on AJK? What is the constraint? Okay, I leave it for you to do. Means this is kind of homework problem, right? This problem will meet you again in the exam. Okay. Now AK is done. AJK is done. Let's talk about now P of x given phi k. Now we have a emission probabilities. We want to estimate the parameters of emission probabilities. Now see, you can take any model, any probabilistic model or any kind of PDF to estimate Px given phi k or xn given phi k, right? What models can you take? Gaussian mixture model. What else? Deep neural networks, right? How will you take deep neural networks here? Can deep neural networks model PDFs? Can deep neural networks model PDFs? How?
We just have to be like the sum of the output.
How do you do that?
By using softmax.
Yeah, by using softmax. That's what we do in the classification problems, right? Multi-class classification. We always convert our neural network into a PMF or probabilistic model. So where xn is the output state or output class and phi k are the weights, right? And yeah, that's it. So you have to estimate the P of xk. But in this case, xn is not discrete random variable, it's a continuous random variable. Oh, but zk is a discrete random variable, right? So therefore you can use your, so basically this neural network will have k outputs, capital K outputs, and log pxn given phi k will be simply the kth output of your neural network, and xn is the input to the neural network, right? But you have to apply Bayes rule for that, but that can be done. Convert px into pz, px given z as pz given x using Bayes rule. Okay, so let's assume a Gaussian PDF. Let P of xn given phi k be a Gaussian PDF. Okay, then if that is the case, then what are the estimates of mu k and sigma k? Can you estimate mu k and sigma k now? Like you want to maximize the Q with respect to mu k and sigma k. So this phi k is basically mu k and sigma k. A Gaussian distribution. Can you find the mu k and sigma k now? Huh? Yeah. That's the standard Gaussian MLE. MLE for a Gaussian PDF. So this will come out to be, your mu k will be equal to, in general, what is the mu k for a Gaussian distribution? This is the mean of the data. This is the mean of the data, right? Sum over all x divided by number of terms, right? But since here you have gamma terms also, it's a weighted mean. You can derive it the same way you derive the Gaussian ML estimates. Similarly, you can derive for here. You will get this to be equal to so the weighted is the weighted average of xn, not the average but the weighted average. And likewise the sigma k, if my x were a vector, then sigma k would be this is simply summation over all n, the weighted average of the covariance. Right? Simple Gaussian parameter estimation. Okay, that's it. So basically M step was very easy. The maximizing the loss function with respect to the parameters, that step is very easy. Now what step remains is the E step. How do we compute these expectations, or this gamma and sigma? So the E step means in the E step you want to estimate gamma and zeta. So let's start from the definition of gamma. What is gamma Zn? Gamma Zn is Q of Zn given x comma theta old. Right? Now see, when I say Zn given x comma theta old, it means the P of Zn given x and the previous parameters. Right? We have already seen that. The Q is same as P. Right? Just P with the previous parameters. Right? Theta is no more a variable, it is fixed to the previous values of theta. Right? Theta is fixed here. So here now, if theta is fixed, I want to calculate probability of some z given the data and the thetas. It's just like the inference problem, right? It's just the inference problem. So in the E step, we just have the inference problem. Model is given to me. I just want to find the membership functions or probability of z. Okay, so let's simplify it. How this simply inference problem, you already know how to solve the inference problem. Zn is a single random variable, categorical random variable. How do you estimate qz given x from the HMM? How do you estimate qz given x from the HMM inference problem? Huh? Using Bayes rule, right? You don't know what is qz given x, but you know what is qx given z, right? So let's use the Bayes rule. This becomes equal to q of, I'm again omitting theta old because it's obvious that it's theta old is given to us, times q of zn divided by q of x. Now this capital X is actually all the variables x1, x2, x3, so on up to x small n, then x small n plus 1, so on up to x capital N. It's the whole series. I will just draw it once here. So this is z1, z2, z3, so on up to somewhere in the middle you have zn, then you have z capital N. And in the outputs, you have x1, x2, x3, xn, x of capital N. Right? This is your hidden Markov model. And you are computing gamma at some zn. At some zn, right? Probability of this zn given all the x. Okay. So how should we proceed now? Now I want to find probability of all the x given only this zn. That's a very strange kind of inference problem. Huh? How do we solve it? How do we factorize this qx given zn? All the x given just one zn in the middle somewhere. How do we find this? So what we do is, let's break it like everything from here to here and then everything after this, right? That's the only way we can do it. So how we break it is, this is equal to q of x1 so on up to xn given zn times q of xn plus 1 given so on up to x capital N given zn into q of zn is anyways there, divided by q of x is also there. Is this step clear? How we broke it into two parts. Everything from here till xn, and then everything. So see, this term should have been this given these terms, right? But because of conditional independence, if Zn is known, then this becomes independent of the previous xn's. Right? That's why we wrote it like this. Now what we do is, we combine these two. What will it become? Q of x1 so on up to xn comma zn times q of xn plus 1 so on up to x capital N given z small n divided by q of x. Now let's call the first term as alpha n, alpha of zn, the second term as beta of zn. We will see that these terms now kind of iterate. Iterate means for any n, you compute this term, divide by qx. That is my gamma zn, divide by qx. Now let's see what is this alpha Zn. I want to compute this term, right? I don't know how to compute this term. In the inference problem, I don't know how to compute this term. So let's focus on this term now. Alpha Zn is defined as Q of z x1 to xn comma Zn. Now, how we compute alpha Zn? We do it in an iterative fashion. Okay, first tell me what is alpha Z1? What is alpha Z1? It's simply Q of x1 comma Z1. What is this? What is Q of alpha x1 comma Z1? Q of x1 given Z1 into Q of Z1, right? This is simply equal to Q of x1 given Z1 into Q of Z1. So what is this? Q of x1 given Z1 is simply the probability of x1 given phi of Z1, right? Of the old parameters, right? Okay, this is the old parameters. Times, what is Q of Z1? It is pi k, pi Z1, old. That's it. So you know how to compute alpha Z1 from your HMM. Now how do we compute alpha Z2? Alpha Z2 will be little complicated, huh? You will have x1, x2, z2. So what we do is we can define it iteratively, which means I can compute my alpha Z2 from alpha Z1. Then I can compute my alpha Z3 from alpha Z2. Just iteratively. Let's see how we do it. So alpha Zn is Q of x1 to xn, Zn. Right? I want to express alpha Zn in terms of alpha Zn minus 1. What do I need? I need xn minus 1 and Zn minus 1. I have xn minus 1 somewhere here, but I don't have Zn minus 1. How do I introduce Zn minus 1? In the PDF, how do we introduce Zn minus 1? Marginalize. Very good. So we just say comma Zn minus 1 and marginalize over Zn minus 1. Right? So now let's try to break it in terms of alpha Zn. What do we need? I need everything up till xn minus 1 and I need Zn. Let's write it down. x1 so on up to xn minus 1, Zn minus 1 times Q of xn, Zn given everything else, all the other terms. Right? Now, if I know Zn minus 1, do I need anything else? Because my xn depends on Zn, Zn depends on Zn minus 1, it's independent of all other xn, right? So this term actually is equal to Q of xn, Zn given Zn minus 1 only because of conditional independence. Right? Right? Now, let's write it in terms of alpha. Oh, there is a summation of Zn minus 1 here. Summation over Zn minus 1. What is this term? This is alpha of Zn minus 1. Right? This term is alpha of Zn minus 1. What is this term? Q of xn given Zn times Q of Zn given Zn minus 1. Right? That's it, done. So this is how you can compute alpha Zn from alpha Zn minus 1. The simple rearrangement of your terms so that you can compute it very efficiently. Now you know what is Qxn given Zn. This is simply the emission probability. What is Qzn given Zn minus 1? Transition probability. You know these numbers, right? You know that this thing is equal to A Zn minus 1 to Zn. And this term is simply your P of Xn given phi of Zn old. This is also old. Right? You already know these values. Okay, so in this way you can compute your alphas. Now let's see betas. What are betas? So my beta of Zn so if you, okay, first let's see what is beta of Z capital N. What is beta? Beta is Q of everything up to capital N. Oh, this given Z capital N. So this is simply X P of or Q of X capital N given Z capital N. Right? This is my beta. Beta of Z capital N. Do you know its value? Do you know what is Q X capital N given Z capital N? We're at the far end of the chain. What is the value? Emission probability. Right? This is simply the emission probability. So you know beta Z capital N. Given this, can you compute beta Z n minus 1? Z capital N minus 1. That is the question. So we can use this iterative formula to compute beta Z n minus 1. So, and this iterative formula you will derive. I'm not doing the derivation here. It's done exactly the same way as you did for the alpha. This is also a problem which you may see in your exam. Right, so it is simply the emission probability at n plus 1 and the transition probability from n plus 1 to n. So you're going backwards now in the chain. Right? In this iterative fashion, you can compute compute beta Zn for all the n for all the k's. Right? So tell me what is the dimensionality of alpha? Alpha is a matrix. What is the dimension? N cross k, right? Right? For every n, it takes a value and Zn is a vector. So which means Znk. So which means it has k values. Likewise, total n cross k matrix. Beta is also n cross k matrix, and you compute it. Alphas are computed starting from alpha Z1. You go forwards, and betas are computed starting from beta Zn. You come backwards. In this way, you can compute all these values. And you can represent your gamma, or you can compute your gamma from alpha and beta. And likewise, you can also compute your zeta from alpha and beta. So what is zeta now? Let's see the whole E step is to estimate gamma and zeta. We have estimated gamma in terms of alpha beta. Let's estimate zeta now. So what is my zeta n minus 1 comma Zn minus 1 comma Zn? This is equal to Q of Zn minus 1 comma Zn given X. Again, an inference problem. This is also an inference problem. How do you do this inference? Using Bayes rule. Let's use Bayes rule. This becomes Q of X given Zn minus 1 comma Zn times Q of Zn minus 1 comma Zn divided by Q of x. Right? So let's consider the first term here. Q of x given Zn minus 1 comma Zn. This term can be written as, again break it up into two parts. One is the up till n minus 1, right? This is a chain. This is Z capital N, this is Z N. So Q of capital X given Zn minus 1 comma Zn. I can take everything up till n minus 1. This is equal to Q of x1 so on up to x into Q of xn given Zn into Q of xn plus 1 onwards given Zn. It need not depend on Zn minus 1. If Zn is given, then you don't need Zn minus 1. Okay, this is the first term. What about the second term? The second term is simply Q of Zn minus 1 into Q of Zn given Zn minus 1. Right? Now, this term is this. So what are we trying to do? We're trying to represent them in terms of alpha and beta. What is alpha? Alpha is all the x up to some n into z of that n, right? And here we are seeing this is something like alpha, all the x up to n minus 1 comma Zn minus 1, but there is no comma, there is rather a given, so we can convert it into comma also. How? By multiplying this with Zn minus 1. So these two terms can combine to form alpha. So these two, this is equal to alpha of Zn minus 1, right? This term and this term combine to form alpha. And what about this? This can be written in terms of beta. So what was the beta? Beta was defined as starting from n plus 1 onwards given Zn. So xn plus 1 onwards given Zn. This term is exactly beta. So let's write this also. This is equal to beta Zn okay. What is remaining now? So Q xn given Zn is remaining, and Q of Zn given Zn minus 1 is remaining. So this is my zeta. That's it, right? I know alphas and betas. This is simply the emission probability, this is simply the transition probability. So therefore I can compute my zeta also from the by simple inference, right? That's it. So in this way we can compute our parameters of HMM. So how we do is we first compute gamma and zeta using E step, then we fix them and update our parameters, update our model. Then again we re-estimate our gamma and zeta, again update our parameters just like we did for k-means clustering. Similarly, we keep updating our model parameters. This is what is hidden Markov model. Do you have any questions? Do you have any questions? No?
Is it necessary that with the number of iterations will increase, so model performance always gets better?
Yeah, good question. The question is, when we are iterating this E and M, is it guaranteed that our model will improve, or the loss will, or the value of Q will increase, or the loss or the likelihood will increase? Is it guaranteed? When we are doing these iterations, is it guaranteed that our original likelihood will improve? No, no. But means it will improve to a maximum, means it will improve and reach a maximum. That is guaranteed. Is it guaranteed? How? That's the proof of EM algorithm, right? EM algorithm always improves your likelihood, right? That proof is there. Means that's the way EM algorithm works. It always improves your original loss function, right? If you remember roughly, you have some original loss function which is very difficult to compute. So what you do, you fix your parameter here. This is the parameter theta. You fix your parameter and compute a Q function here. Then you maximize your, so not like this. Actually, this Q function is such that it has its, at this point, let's say my slope will be same. This is my Q function. The slope is here the same. And then when you maximize your Q, you obtained a new theta, the theta 2, let's say. This was my theta 1 where I started. At this theta, my original P function or the L function is better, right? I have improved my L. Then I will again create a Q function which has its tangent matching here. This is my new Q function. And again, when I find the maximum using likelihood step, then again I have improved my L, right? So maximizing Q is the M step, and then shifting my Q is the E step. So in this way, EM algorithm proceeds and it will reach the maximum of L. It could be a local maximum, that could be a problem, right? So we are not saying that it will attain the global maximum, but at least local maximum it will attain. All right? What's the time? Time is up. Okay. Fine then. I have some logistical questions. Just give me a moment.